Hi, welcome to our discussion of electrophysiology of cardiac cells. We're going to do two movies, one that discusses the physiology of pacemaker cells and the other that discusses the physiology of cells that are going to contract, so the cardiac myocytes that actually contract. So if we look at this diagram of the cardiac conducting pathways, we'll see that we have quite a few different cells that each have distinct electrical properties. And these distinct electrical properties are present because these cells have different channels that are allowing different flows of ions into and out of the cell on different time frames. So sometimes those time frames are called kinetics, so how long does a channel remain open, at what time does it close, and so forth. So the two types of channels we really need to discuss in order to understand what's going on in the heart are pacemaker cells. And so recall that the pacemakers are the SA node, the AV node, and in fact, some of the cells that are found in the Purkinje cells, the Purkinje fibers, also display pacemaker function, although it's typically not that important for heart function. And of course, we have other cells that are slightly different that are just going to contract and display slightly different currents, and those would be contracting myocytes in the atrium and contracting myocytes in the ventricle. So we're going to focus on pacemakers first. Now, as we go through both lectures, we are going to talk about flows of ions, and when we talk about flows of ions, we often refer to those as currents. And if we go to the equation that is used often in electricity, studying electrical fields, V equal IR, the big I stands for a current or a flow. So often on these diagrams, we're going to talk about a current of something. We'll use the big I for current, and then we'll talk about, well, this current involves sodium, so it's a flow of sodium. So I would say an I and A. Or it could be a flow of potassium, or it could be a flow of calcium, right? These are all valid currents. I'm not really saying anything particular about the proteins that are carrying these currents. I'm just saying there's a flow of calcium, right? It could actually be multiple channels that are causing calcium to flow. The sum result is this flow that we're observing. So let's jump in and start talking about the pacemaker, specifically the SA node. And the SA node, left on its own, is going to fire at something like 100 times per minute. And so what we would see is a stereotypical depolarization, repolarization, depolarization, repolarization that would occur 100 times a minute. So let's talk about the currents that allow this to happen. On this chart, I have a chart that shows us the voltage. And for these cells, they're going to run somewhere between minus 70 and, let's say, plus 15 to plus 20 millivolts. And I have two lines here. And these two lines represent thresholds. And thresholds are going to be points at which a voltage-gated channel will open. If you recall back to talking about skeletal muscle or the action potential in neurons, we've talked a little bit about the concept of threshold before. What you'll notice in this diagram is a little bit unusual, is that there are actually two different thresholds, and that's going to be important for the function. So we're going to walk through a typical cycle electrophysiological action potential that would be generated by the SA node. And we're going to start off by having a current that's going to open up because we reach this higher threshold of minus 40 millivolts in this case. And so what's going to happen is we're going to see the cell become positive as positive charge enters the cell. That positive charge is actually a calcium current. So this is the ICA. Now, you might think calcium entering a cell that's a muscle cell, well, that would probably cause the muscle to contract. And you would be right if you're talking about skeletal muscle or most cardiac muscle. But in these pacemaker cells, they really don't have the cellular machinery that underlies contraction. So here the calcium is purely mostly playing an electrical event, right? It's causing the cell to become positive. So this channel opened it up because it's voltage gated. It's reached threshold, so this channel opens up. And like a lot of other channels we talk about, that channel does inactivate, right? Meaning that it stops the flow. So it stops it so that no more calcium can come in. And at this point, another channel opens up, right? This channel was also triggered by this first threshold, but took a little longer to open up. And that channel that opens up is carrying a potassium current. So that is IK for potassium current. And as potassium leaves the cell becomes a negative. It's at this point that something a little bit unusual happens. And that is that as the cell becomes more and more negative, it actually approaches a second threshold. And this second threshold is going to, when we reach that threshold, we're going to have another current open up that's going to slowly cause the cell to become more positive. And so this is because sodium is flowing into the cell. And making the cell more positive. This current is unusual. In fact, we call it the IF current. Right? And of course here we're letting sodium into the cell, so the F doesn't stand for sodium, and there's no other ions that would really be accounted for by this. So the F here stands for funny. So this is the funny current. And it's called the funny current because this is the first example of a channel opening when the cell became too negative that people discovered. So prior to this, all kinds of voltage-gated channels had been discovered. They always open when the cell became positive. Here's one that opened when the cell became too negative. So a very peculiar or very funny type of current. So of course, if we start causing the cell to become positive again, at some point we reach the threshold for the first current, and we can really just repeat the process over and over and over again. So what makes pacemakers so interesting is that they have this effect where the threshold is reached, which really sets up a condition that allows us to reach the second threshold, which sets up a condition which allows us to reach the first threshold, and so forth. So it has an intrinsic automatic firing pattern. And again, if we're talking about the SA node, that pattern is something like 100 beats per minute.